right, hey there. So this is the first of our kind of series of videos for this particular chapter that have to do with, this part has to do with acid-base theory. So there's going to be a sequence, I'll put it back up here. There's going to be a sequence of about 5 videos or so that kind of relate to some of this acid-base theory stuff. This is mostly introduction, and in class, a lot of what I'll do is be kind of going into a lot more in-depth stuff on this. So you kind of think of this as a way to support what's in the textbook, support what we're doing in class, sort of introduce those basic concepts. Because in this particular unit, I'm definitely pulling things from a variety of different chapters and a lot of different concepts to kind of put into this context of acid-base, because we can use acids and bases as a way to learn a lot of different chemistry that's in here. So I'm going to be picking a few topics. So you can kind of see what the sequence of 5 or so videos is that has to do with this part. So this one right here today is about definitions of acid-base theory, or different models of how acids and bases were pictured. And then we'll get into some of the other ones in the later videos. So you can kind of see the sequence there. So this particular one right here is just kind of defining what is an acid and a base. What are they? How do we envision them? And then we're going to talk a lot about the Bronsted-Lowry model, I guess, here in this particular video. That's kind of our big, get this out of the way here, our big idea that we want to try to get that out of the way. Get my pen here. So Arrhenius, the very first one that was up here, this guy that's up at the top, Arrhenius, he was our basic. Our basic dude. He's the one that kind of knew how to do this. He was the one that first identified it accurately. There's plenty of people that talked about acids and bases before Arrhenius did, but he was the first one that really kind of got it right in the sense of what it was. So he defined it really simply. He defined an acid as something that contained hydrogen ions, and he defined a base as something that contained hydroxide ions. There we go, if I get it right correctly. And again, that works for many, many, many things that we do in chemistry. And if that's the one model that you can, have room for in your brain, that's a pretty good definition. And you're talking about like 90% of acid-base behavior can be explained by Arrhenius's model. And it was only a little bit, a bit later that folks started to realize that acids and bases there were some things that acted like acids and bases that didn't have a hydroxide in them specifically. The hydrogen one's still pretty good. Like, even if we look at the modern versions of it, all acids contain hydrogen. It's the bases containing hydroxide part that actually caused the issue. It's always bases are the trouble. They're so basic. Anyway, that's where the issue kind of came into play. So coming along a little bit later was these two guys. And this is actually 2 different people. This isn't one name hyphenated. It's actually a person named Bronsted and another person named Lowry. By the way, Bronsted's name is spelled with this kind of O. And I can't figure out how to do that on notebook software. So that's literally what the letter is supposed to be in there. But these 2 guys took that same idea and they sort of broadened it a little bit. So the way that they defined it was that an acid is a proton donor, which is DONOR, which is essentially the same thing as saying a hydrogen. Remember what a hydrogen atom is, right? A hydrogen atom is a proton with a single electron around here, right? That's it. That's all a hydrogen is. So if you're talking about a hydrogen ion, well, a hydrogen ion has lost that electron. So that literally is the same thing as saying a proton. That's all a hydrogen nucleus is just a single proton. There's no neutrons present. So literally defining an acid as a proton donor. It's the same thing as saying that an acid has a hydrogen ion to it. What was different here is the way that they defined a base. And they defined it in reference to this. So if an acid is a proton donor, then a base is a proton receiver. Receiver, E-I-V-E-R. They're the ones that can get the proton, say, from an acid that's donating it. So that's kind of what we'll take a look at on the next couple of slides here and look into more detail. And then actually got quite a bit more acid-base behavior is covered by the Bronsted-Lowry thing. So the Bronsted-Lowry model is more of an extension, I guess, of Arrhenius's model. It doesn't mean that Arrhenius's model is incorrect, not at all. It just adds to it and generalizes it a bit more to cover to cover more cases. And then this third one, I'm just going to mention this very briefly here. We're really not going to talk about it at all here in Chem 2, but I just want to do this for the sake of letting you know that there are additional models. So the Lewis model is actually an extension yet of Bronsted-Lowry in a sense. And this one focuses more on electrons, electron pair receiver. And I'm never going to test you on this, so don't worry about it too much. R-E-C-E-I-V-R, I can't spell. And then, so this would be an acid, and then an electron pair donor would be a base. So again, there's just a couple of different ways that people have conceptualized what an acid is and what a base is and how these sort of things behave. So again, my whole point in bringing up the Lewis model here was not to go, oh my God, here's another thing I have to learn, but just so you know that there are other models that's out there. So we're really going to be focusing a lot here in Chem 2 on the Bronsted-Lowry model. That's really our basic model, our main model that we use. So how do these things work? So Bronsted-Lowry really focused not only on what an acid and a base is, but how they behave and how they behave when you react them together. So this is a typical acid-base reaction right here. You've got HCl. That indicates that we've got our acid, right? That's a really clear indicator that that's a base, even with Arrhenius's model. So we've got hydrochloric acid and sodium hydroxide. And when these things interact together, when they behave together, they will usually do sort of a neutralization reaction is one way to think about it. This isn't always true, but a double displacement reaction of a sort is how these things kind of work out. And so what we've got here is that we would typically form double displacement like this, right? Our two exchange of ions. So we would get this NaCl and HOH. That's also known as water. It's really common with acids and bases that this is what you get, something that we would call salt. This is the common salt that you know of as table salt, but then we also get water. And I'm writing it as HOH here rather than H2O because a lot of times when I write it in this format, it's really hard to remember that the structure of this is a hydroxide ion bonded to another hydrogen, and that's where the break happens. So that's why I typically write it as HOH in this context. But what's really happening in here? What's really happening is most of the time these things are in solution, right? But if you think about this in terms of acids and bases, in terms of proton donor, proton receiver, there's a different way that we look at this. So let's take a look at this particular piece right here, the HCl. Notice how it's got a hydrogen with it. And then on this side, the chlorine does not have a hydrogen with it. And you really think of it this way, it's sodium ions and chloride ions. The sodium ions are really actually a spectator in this particular reaction. So our hydrochloric acid here has donated its proton. It no longer has the proton with it. It's donated this proton to this other molecule. Here it is. It's stuck over in this particular shape. So this right here is our acid, right? And that means that this one here is our base. Because here, this hydroxide is our proton receiver. See, here our hydroxide does not have it, but here, there's that same hydroxide, HOH, it has received this hydrogen, and here it is in this particular case. Now, why did I write it this way? Liquid water, in this particular case, is very strongly bonded together, sort of like a precipitate is. So these two are indeed ions, but this has become molecular. So when you take a look at the ionic equation, you can kind of see that proton donor, proton receiver behavior a little bit clearer. So Bronsted-Lowry also wanted to go a little bit further with this, and let's come up with some ways that we can talk about the before and after of this. Notice how I've got this crazy little double arrow in here. A lot of times these reactions aren't the simple one-way forward reactions anymore. These function more like a teeter-totter, where you kind of have some forward reaction and some reverse reaction. In Chem 1, I talk about it's kind of like trying to build a sand castle with dry sand. Like you keep adding sand to your castle, but the castle keeps collapsing at the same time. In other words, our reactants keep forming products, but our products also keep falling back apart, back into reactants. Our products aren't necessarily super stable. So we call this an equilibrium equation. We'll talk about this more in a future video, but I just wanted to point out why I have this double arrow here as opposed to the single arrow. So what's happening here? If we have HCl and HOH, this is hydrochloric acid, and this is water. Here's our acid, right? This is the one that's got the hydrogen to it. What is this going to do when we put a strong acid in water? Well, it turns out that this acid still acts like a proton donor. We still have a proton donor. It gives away its proton. In a sense, it's as a strong acid, it dissociates, but it's giving that acid away, that hydrogen away. Now, where does it go? Well, it's only got one spot. Now, this is weird. It actually goes to the water. Yeah, what in the hell is that? Bedwell, have you lost your mind? Yeah, absolutely. So water acts as the proton receiver and forms this really weird ion here. It's water with an extra hydrogen to it, and it's called hydronium, D-R-O-N-I-U-M, ion. It turns out that those little hydrogen ions really don't exist by themselves in solution. They will always stick to a water molecule. Every hydrogen that's out there isn't truly just hanging out being a hydrogen. It's a hydrogen stuck to a water molecule. And so for the purposes of what we're doing, we're going to call that a hydronium ion. And so now if you see this right here acts like a base. It's receiving, right? Base like this. It's receiving that proton. So what do we name these things? How do we call these things? Think of it as a before and after. So before, we had this hydrochloric acid, and now after, we just have the chlorine ion all by itself. It's donated. Now it's after it's given it away. So now in this particular case, we call these things on the product side conjugates. So it's after you've kind of messed with it a bit. So this is a conjugate. This is also a conjugate. H3O is also conjugate. ATE, because they're on the product side. So this is sort of after the reaction has happened. We've conjugated them, just like you conjugate a verb in Spanish class or something like that. So we've got our before, and then we have our after. Our before is acids and bases, and our afters are conjugates. But how do we talk about these in that sense of one of these has received and one of these is given away? The easiest way to think about this is like, once this is given away, this acid has given away its proton, now it's sort of swapped sides. After it gives away its proton, after it's acted like a proton donor, it is now what we would call a conjugate base. Another way to think about this is to think about this reverse reaction. If we were to go this direction, how is this acting? The Cl by itself would receive a proton if we're going in the reverse direction. So the reverse reaction is acting like a base. The forward reaction, the chlorine is giving it away, and it's acting as an acid to begin with. So when it's got the hydrogen with it, it's the acid as a reactant. But when it's its ion form as the end of the product, it could be acting as a conjugate base. So our hydronium is the opposite, right? So if it started off as a base, it has received that proton. Now here it is in its received form. And this is the conjugate acid. So basically they swap sides. Whatever was the acid, the base on the left becomes the conjugate acid on the right. Whatever was acid on the left becomes the conjugate base on the right. They swap over. And again, if you take a look at this in the reverse direction, it goes from H3O to H2O, right? It gives away if you're going in the reverse direction. So that's why this conjugate, if you're thinking the reverse reaction, is acting as an acid. So with ammonia and water, a similar but opposite kind of process happens. So we've got NH3 and HOH. In this particular case, ammonia acts like a base. It acts as a proton receiver. So what is that going to look like? Well, if I take ammonia and I give it, right, it receives a proton, it now becomes NH4 with a positive charge. This is the ammonium ion. Okay, this is ammonia, the molecule. This is the ammonium ion. So again, now it is received, right? So this means that this is the conjugate acid, right? Well, where did that proton come from? Well, that proton had to have come from the water. So that means in this case, water's acting like an acid. Water does some weird stuff. Water is going to donate one of its hydrogens to the ammonium. And so what's left over behind is OH minus. The hydroxide is all that's left. And this becomes the conjugate base. And that actually makes more sense because hydroxide is always a base, right? That's an easy one to kind of see. So this is the conjugate base now because this is reproduced as a result. This is weird. I get that this is kind of a weird idea. So let's practice a couple of examples. So identifying conjugate acids and bases is particularly important with some more of this unique acid-base behavior, like weak acids or things that are not obvious bases is where it really becomes important. Strong acids and bases, it's really easy to kind of tell. But with situations like this, it's a little bit more awkward. So here we've got water, and this is carbonic acid, hydrogen carbonate. So if you take a look at this, which one is acting like the acid? Which one is donating a proton? So look at the anions right here. If I look at this carbonate and I look on the other side, here's my carbonate. Here it's with 2 hydrogens. Here it's with 1 hydrogen. That means this has to be the acid and this has to be the conjugate base, right? It's given away its proton. Here's what it looks like after it has done the giving, right? Here's what's left over behind. And so now if you take a look at our other pair, this is our hydroxide pair, hydrogen hydroxide, otherwise known as water. Here it is before, right here, and then here it is after. So here we've got a base, and then this has to be now the received part of it, has to be the conjugate acid. And then here's our last pair down here at the bottom. This one's definitely crazy, right? If you tried to use Arrhenius' model for this, it would be very difficult to tell which one would be the acid and which one would be the base pair. So this is where the Bronsted-Lowry model really helps. So look at your pairs, right? I've got a hydrogen and an OCl, and then the other side I have just an OCl. And here I have this crazy looking thing, C6H5NH2, and then here I have C6H5NH3. So here's got to be one pair, right? This is one pair, and then this is the other pair. So look for the pairs, the left side, right side. All right, which one's acting like the proton donor? Which one's giving away? Here it has a hydrogen, here it does not have the hydrogen. Therefore, this has to be my acid. Therefore, this is my base, right? And if this is my acid, the after version of it has got to be the conjugate base. Right, I'm just going to write CB on that one. This one is the proton receiver, right? 2 hydrogens versus 3 hydrogens. And yeah, you got to look kind of close. So this is the base. That means this part right here is the conjugate acid. And again, this becomes more important when we start to talk about different types of reactions and things like buffering and other stuff that happens. So there you go. This is a more of a deep dive. I believe that's our last one. Yep, that was my last one. This is sort of a deep dive into acid-base behavior and the Bronsted-Lowry model of how acids and bases work, especially for things that don't have hydrogen and hydroxide. So there you go. I hope you liked it, and I'll see you in the next one.